Cool. But
Plus, you like it.
Protein bar.
I don't like it. I don't really see it all. Yeah, I don't have any seats.
I hadn't even
I
noticed.
was just kind of hanging out.
So we got those.
No.
Whereabouts?
Central Pennsylvania.
Oh.
Yeah.
Yeah. Ha. Checkmate.
It was cool. I was there for like a couple days.
Got you.
It was sunny for one of them, and it snowed every other one.
Size can't explain that.
I also went to New York.
Makes sense.
I thought it would be more fun than it was.
Are you doing math stuff?
Yeah, a little more math stuff.
Okay.
Yeah, last time we did a fair amount of math stuff, and I just want to draw your attention to these two references I have for big O notation. And certainly if you weren't here the last Friday before break, you should watch the video because we do a few examples of analyzing various algorithms. And along those same lines, in preparation for this day, exam 2, I've got some big O exercises here just to make sure that everybody knows what to expect on an exam, for example. You should be able to analyze a particular algorithm, couple of loops or what have you, and tell me whether, what order they are. Are they big O of 1, big O of n squared, what have you?
It's fairly reasonable to assume all n's are integer values.
Yes.
Okay.
In this notation, n is invariably an integer value. In fact, it's a natural number. Okay. Huffman. What does it do, Friday?
Yeah.
Yeah. Definitely want to start that if you haven't done so already. It's not one that you're going to be able to sit down and write in, just, yeah. In fact, it's not even one that you're going to be able to sit down and write in 12 hours of coding. You got to be able to write a little bit and walk away because this thing will drive you crazy. So you've got to do it in little pieces.
Big O exercises due at some point? Or
No,
just there?
not at all.
Because they're in the homework category. So I guess.
It's a good point, yeah. But don't turn them in.
She looks like I'm not going to look at it.
Exactly. No, the math that we're going to do today is somewhat unrelated to that. The reason I wanted to get that big O notation in there is we're about to move into 10 days of sorting. Not today, but maybe starting Wednesday, about 10 days worth of sorting. And we're going to do traditional sorting methods, and then we're going to do some recursive sorting algorithms, the biggie being quick sort, which is a really fun algorithm. And then we'll finish with a tree-based sorting algorithm called a heap sort, which is the only algorithm of all of these that is reliably less than order n squared. The heap sort is order n log n. Yes?
The XKCD ineffective sorts.
Oh, yeah.
I'm sure I have. It sounds familiar, but...
Boom.
Oh, yeah. Yes. I like some of these down here.
Have you seen Sleep Sort?
Yes, that is beautiful.
Sleep Sort's amazing.
Is that also?
You run thread sleeps in order to have the numbers print out in the right order. You sleep for the number of seconds according to the value, and then print it.
Nice. Nice. And how many threads are you allowed to have?
A lot.
A lot. Okay.
Very large number.
That's the only real rate limiter there would be. Yeah, I like that. Where did you see that?
I can't remember.
It was on the SKCD forums.
Was it?
Was it
no,
also-
I saw it elsewhere though.
Yeah, well, if it's in the forums, it's probably floating around out there. But no, I've not seen that one. That's cute. All right. So that's where we're headed. Today, I want to finish Huffman with a fairly extensive, I don't know, we'll see how far we get. I want to prove, essentially following David's notes, prove that the Huffman tree is the best possible encoding, at least for codes with the prefix property, codes that can be represented in a binary tree. So as we discussed earlier, for example, fixed length codes like the ASCII code are not, what's the word? They're not prefix codes, right? They work by virtue of their fixed lengthedness, and there's this correspondence between these 8-bit integers and the character that they represent. So that's a fixed length code. The Huffman code, as we've seen, gives short codes to very frequently occurring characters and long codes to infrequently occurring characters. So it's a variable length code. And if you're going to have a variable length code, unless you've got some sort of really weird overhead kind of system, you've got to have what's called the prefix property. In other words, no code of length n can be extended to a code of length n plus 1 or greater. And these things naturally are represented by binary trees. I suppose you could generalize the notion of code and use more symbols other than 0 and 1, maybe 0, 1, and 2, and have tertiary trees. But let's just keep it simple. So in that case where you're thinking about codes with the prefix property, variable length, so that they're represented by binary trees, we're going to show that the Huffman code is the best possible. And this involves proof by induction. So all you math people out there, you'll be right at home. Yay.
Are we doing the tricky induction where it's like, by induction, this is true, like we'll split it up, and then we've already assumed that it was true, and so it's true?
We are going to do a very traditional induction where you have a base case, and then you assume everything up to n minus 1 is true, and then prove the end case. So no tricky inductions. So we want to answer this question: is why is Huffman optimal? And we have to be careful about what we mean by optimal. This is among codes, variable length, prefix property. And all of that is just shorthand for saying that the code resides in a binary tree.
So wait, we're asking why is it optimal for compression and among possible solutions involving a code which can be
Exactly right, yes. Involving compression. So for example, we'll use some notation here that David introduces. The weight of a tree is essentially the sum over leaf nodes, V, the depth of the node, times the weight of the node. And if you look closely at this, okay, so let me label some of these things. This is the depth of V, and this is the frequency of V.
Depth is a number of ones or zeros.
Exactly. How many edges do you have to cross to get from the root node down to this leaf node? And so as Josh just pointed out, this is the thing that we want to minimize, right? Because WT is essentially the bits in the compressed file, right? Because DV is how long a code is, is how long the code is for V, and WTV is how many V's there are in that file. So you just multiply those guys together, you add them up, and that's how many bits are in the compressed file. Agreed? Okay. There's a bit of I don't want to call it an abusive notation, but there's a bit of contextualization that goes on here. When we plug a tree into the weight function, this is what we mean. And when we plug a node into the weight function, what we mean is how often did that leap occur. And
It's an overload.
it's an overload, exactly right. I'm trying to think if there's in some sense, it just occurred to me, if in some sense they're equivalent, yeah.
They are if you define the depth to start at 1.
Exactly.
But
Which
then
makes
that's a recursive definition, which is kind of...
Yeah, that's a good point too. Let's just not think about it too much. Okay, so we want to minimize this guy where we're summing over leaves. So not interior nodes, just leaves. All right. So before we get into the proof, I want to do some preliminary algebra. And that's if we're given a tree, and if I say tree, and I don't use the word binary, I mean binary tree. So given a binary tree, what's the effect of swapping two nodes? Could be a leaf, could be an interior node. What's the effect of swapping two nodes on the weight of the full tree? And the picture that David has in his book, and I'll kind of sketch it in here. Here's a binary tree with the root node right up here, and inside is just filled with nodes. And then let's say we have V sitting here and say W here, and we've got the subtrees associated with those guys. What's the effect on the weight of swapping V and W? So this is the full tree T. And inside, you can imagine, right? There's the tree that sprouts from V and the tree that sprouts from W, and they're non-intersecting, right? They're non-intersecting, and so swapping them is really just a matter of just taking V and moving it to the node where W is, and taking W and putting it where the node V is. That's it. Everything else stays the same.
So is the weight of tree W times the depth of W of V minus W?
Yeah, so we've got to introduce some symbols, but you're getting there, and we'll just derive an explicit formula. But we've got to introduce these depth variables. We need to know how deep V is and how deep W is and how much V weighs and how much W weighs.
Deep V, deep W.
Yeah. So let's do that. So notationally, we're going to let dV be d1, and we'll let dW be d2. First, it follows that the depth of x is just, let me see here, is just d1 plus the depth of v with respect, the depth of x with respect to v. So this is in the, so I'm sort of generalizing this d function, this depth function, so that dv of x is down here, say. Right. So, and that makes sense, right? You've got the depth of v, and then you've got the depth of x with respect to v. Okay, and let's see here. So if we, gosh, I don't like this notation. I'm gonna introduce some new notation on the fly and hope it doesn't get me in trouble. I'm gonna let SV be the subtree at V. Does that make sense to everybody? So it's one of these little triangles. This is SV. Let's do the weight of that tree. The weight of that tree is the sum over the leaves in the tree d, the depth of x with respect to that tree, and times the weight of x.
Would that be the depth with respect to V?
No, it's the depth, yes, exactly. Exactly. And we'll figure out from context that that's the depth with respect to V because we're working on this tree right here, and so there is no other tree, in a sense, in this universe. All right, we can... And as soon as I said that, there is... So I know that I can write the depth of x, so that really is the, good gravy. See what I get for doing this stuff on the fly? Let's forget about this for a little while. Maybe I'll come back to it. So I'm going to sum over the leaves in the subtree V. I guess I could keep that, I don't know. And this really, I guess this really is kind of the depth function of t. Yeah, let's do that. Because then it lets me go to here. Okay. Now I'm going to distribute the sum. I'm just going to sum over x here, and you can figure it out from context. D1 weight x plus sum x dv x weight x. Okay, and I'll pull the d1 out, and I have the sum over x weight x plus the sum over x dv x weight x, like that. Now, the sum of the leaves below v is the sum of the weights of the leaves below v is just the weight of v. Right? Remember that when you join two nodes, underneath another node, the weight of the new node is the sum of the weights of the nodes that you're joining. So, screwing around with a little bit of algebra, we see we get this identity. And similarly, we get, if we go over the W subtree, we just get a D2 there. D2 and a weight of W, and the sum dW x weight x, like that. So you get these two formulas. one for the stuff below V and one for the stuff below W. And you can see the differences there make sense. So what's the effect of swapping these nodes? Let me make sure I've got my... So I think I'm going to assume here, figures I drew my picture exactly the opposite, but I'm going to assume that this is V and this is W, because I'm going to assume that D1 is less than D2. That's safe to do, because if that's not the case, then I'll just relabel and switch V and W. I'll just change the labels on V and W. So I'm just going to say V is the one with lower depth. So that means D2 is greater than or equal to D1. They may be peers. So what's the change? What's the net change to the weight of the original tree resulting from this swap? Well, you just subtract these two guys, and you get the expression D2 minus D1 times the weight of V plus D1 minus D2 times the weight of W. And that simplifies a bit to D2 minus D1, weight of V minus weight of W. Let's think about this a little bit. If they're the same depth, what's the effect of the swap? No change. Let's look at some other things. We've got our assumption is that D1 is less than D2, or less than or equal to. So if D1 is less than D2, what can we say about the weights of V and W and how they affect the net change?
It's greater than, or if the weight of V is greater than the weight of W, then you increase the weight of the tree.
Mm-hmm. And does that make sense? Because I'm taking a heavier tree and moving it deeper into the full tree. Moving that guy deeper into the tree does what to its codes? Makes them longer. It's bad to move heavy stuff deeper into the tree because you get longer codes requiring more bits to compress. So this is an important relational equation qualitatively for us to help us understand what's going on. We don't want to move heavy trees down, heavy subtrees down in the larger tree. So if D1 is less than D2, it's best to move heavy trees up. All right. So now that we've got this notational framework, and we've got this nice understanding of how moving subtrees around in the larger tree affects the weight of the tree, we're ready to prove that Huffman is optimal. So we're going to do this by induction. So we'll show that the Huffman trees are minimal weight via induction. Our induction is going to involve swapping subtrees. So remember how induction works. You prove the base case. And then you assume all cases, let's call the base case, say, n0. All cases k, n0 less than or equal to k less than or equal to n minus 1 are true. And then you have to show we have to use these assumptions to show that the k equals n case is true. So we're allowed to assume all the cases from the base case up to the n minus 1 case, and then we're allowed to use whatever information that gives us to prove the n case. And once we've done that, we've proven this for all possible values n, the magic of induction. The base case in our situation the base case is 2. And the reason for that is what follows is going to rely on me swapping subtrees. And if I'm going to swap subtrees, I need at least 2 of them to swap them. So I'm going to start with the base case 2. This isn't really difficult. If I have 2 leaves, what does the tree look like? What's the binary tree look like? It's like a triangle, right? So with 2 leaves, and I should say that n in this case, or k, is referring to the number of leaves. Let me make that explicit. So with 2 leaves, we have essentially, and I'll defend this statement in a minute, we have essentially 1 binary tree. Ignoring left-right. It's perfectly fine to think of a binary tree without thinking about left or right children. All that's really important in a binary tree is that every node has at most 2 children, and we don't really care whether they're on the left or the right.
Well, and switching left to right nodes keeps the weights the same. They're all the same.
Yeah, so what I want you to do is think about sort of this slightly more abstract tree where all you care about is parents and children, right? Who's my parent? Who are my children? And not whether this is the left child or the right child. So in this case, there's 1 binary tree with 2 leaves. So Huffman is optimal because there's only one. Because there's only 1 binary tree. And we know that Huffman, right, has this ambiguity between left and right. Whether you decide to go left or right, you're getting essentially the same code. Whether you decide to call left 0 or left 1 is somewhat arbitrary. It's really just that we have to call left something that's different from right. And so that's why it's safe to ignore that, and that's as far as I'm going to go with that. It's a syntactical or lexicographical kind of thing. All right, let's keep going. So we've proved the base case. Here's the induction hypothesis. The induction hypothesis says that among all binary trees with k leaves, and k is between n0, in this case 2, and n-1. The Huffman tree with k leaves is of minimal weight. All right, and where do we go next? We let TH be a Huffman tree with n nodes, or n leaves, excuse me. That's the very next one, right? So we know that the Huffman trees are minimal for all trees, leaves up to n-1. And now we want to look at the next one. And somehow we want to knock this guy down to the n-1 case, which we know is true. Somehow we want to knock it down.
Can we just look at either of the trees of depth n-1, say that we know that those are both optimal, and then all we have left is a tree, like the same tree we started with. This has a group of two.
So before I try to figure out what's wrong with that proof, let me step back and your gut should make you think that that can't work.
Yeah.
Why?
I don't know, it just seems
Because it doesn't involve Huffman-ness at all.
Yeah.
Right? So there's nothing about Huffman there at all. So I'll just leave it at that and try to think about where it breaks down afterwards. But I'll keep going. Somewhere at some point in this process, we have to invoke what it means to be a Huffman tree. And we will in this approach that I'm about to show you. So let me think about that again really quick. So you've got two minimal trees.
You're saying you basically look at the tree without W, right?
Yeah, it's the two different trees.
But then, like, right, if those trees, like, if one tree has, like, the smallest number of characters is 3, and another is the smallest number of characters is 7, maybe the 7 might have a shorter path than the 3 when you put them together.
Well, I think this might be what you're saying. It seems like when you build this Huffman tree, now you've arbitrarily chopped it somewhere, and you would have to assume that you made two Huffman trees with different data sets. You didn't take all of your data into account when you built it.
Right. When we chop those two guys up, that's it. Yeah. We don't know that those two subtrees are Huffman trees.
Yeah.
Yes. That's easy enough. Thank you. Okay. TH be a Huffman tree with n leaves, and let's say let TM be a binary tree with the same leaf weights. Let me see how I'm going to write this with the minimum possible value. Okay, so we're going to introduce TM, which stands for T minimizer. So the Huffman tree may not be the minimizer of this weight function, but there is certainly some binary tree out there that minimizes this weight function. How do I know that? That there's some guy out there that minimizes the weight function?
You just make the tree such that all possible switches increase the weight function. So find a switch that shrinks it, you do the switch.
Yeah,
or the whatever principle that I'm trying to think of that says that
yeah.
any set of positive integers has the least.
I'm looking at you, real analysis people. Yes. Or did you have it yet, Evan? No. Okay, but you haven't had it either. Oh, has anybody had it? Oh, bummer. Anyway, yeah, the principle of well ordering says that there's a minimum value, right? This is a finite set, and so I can take all of the binary trees with n leaves, however many there are, and we could count them, and plug them into the weight function, and I get a finite collection of numbers. Take the smallest one. Take the tree that gives the smallest one, and there may be many trees that give the smallest one. Pick one. That's what TM is. So we're going to let TM be a binary tree, not the binary tree, a binary tree that minimizes the weight function. And we know that it exists because we're really just pulling from a finite set. I know I made a big deal about that, but in real analysis, that's a huge deal. The existence of a minimizer is a big deal because it's really easy to build a set that doesn't have a minimum value. For example,
integers.
Sure, it's even possible to build a bounded set that doesn't have a minimum value.
Rational numbers between 0 and 1.
Natural numbers between 0 and 1. Love it. Sorry, rational. Yes, there are no natural numbers. Rational numbers between 0 and 1, or in fact, the numbers between 0 and 1 have no minimum. Okay.
Still infinite, right?
Still infinite, yeah. Yeah, you gotta have infinite. If it's finite, then you've got well ordering principle. Yeah. All right. What we'd like to show that the weight of TH is equal, to the weight of TM. I'll put that parenthetically. That's not part of the proof. That's just a statement. This is what we need to do. Okay, here's where the Huffmanness comes in. Let V and W be leaves of minimum weight. So, for example, in the Huff node array, after you've done the sorting, these are the first 2 leaves. I'll even make a note of that. The first 2 leaves after sorting the node array. Everybody okay with that? These are the 2 least frequently occurring characters in the file.
So they're the two with the longest paths.
Exactly. The two longest codes, whatever you want to call it. Why these guys are important is these two guys are going to get joined together. They're going to have the same parent. So in TH, W and V have the same parent. Does everybody agree with that? Think about the Huff node algorithm, the Huffman compression. When you're building the tree, you grab the first two guys, you join them together under a new node, and you insert the node back into the tree. So V and W are siblings. Are they siblings in TM? They're in TM. So TM has the same leaves, right? The same leaf weights. But TM is just this random binary tree that minimizes the weight function. So V and W may not be siblings in TM. Let me draw you a picture. So let's look at TM. Let me be careful here. I'm going to make V shallow. And put this guy here and this guy here. So here's V, and here's its sibling. And then down here, I'm going to put W and its sibling. So V is going to have depth D1, and W is going to have depth D2. But they may not be siblings. All right, if they're not siblings, let's let, right, if they are siblings, then it's not a big deal. If they aren't siblings, let's let the sibling of V be S and the sibling of W be T. And they have their little subtrees associated with them. V and W don't have subtrees, right, because they're leaves. But their siblings may either be leaves or interior nodes. So I'm going to attach little subtree symbols to them, recognizing the fact that they may be trivial subtrees. How can I make V and W siblings?
Switch V and T.
I can switch V and T, or I can switch S and W, right? Okay. Let me read my notes here. I'm getting ahead of myself. So what we're going to do, yeah, let me just put a parenthetical in here so I can remind myself as well as you guys where I'm headed. So we're going to attempt to swap, or attempt a swap in TM so that V and W are siblings. And this will create a new tree called T prime sub M with the weight of T prime sub M greater than or equal to the weight of T sub M. That last statement follows from what?
Minimality.
Minimality, right? TM is the minimal weight tree, and T prime is just some binary tree. So necessarily, the weight of TM is less than the weight of T prime M if I do one of these swaps. All right, let's see what happens. So we're going to try to swap T and V. let's see, if we do that, we can use the net change formula that we derived earlier. The net change then looks as follows. D1 minus D2 D1 minus D2 weight T minus weight V So the net change is necessarily non-negative. Agreed? Okay, let's see what implications that has for us. Moving right along here. So if D1 equals D2, there's no net change. And the swap is okay. All right, let's see. So let's suppose that D1 is less than D2. As I've written in the picture. Then what follows?
Wouldn't it be negative in that case?
What follows about the weights?
Oh. That the weight of B must be greater than the weight of T.
Greater than or equal to, yes. Still with me? Okay. Why is that not really a problem per se? So we know that this is true. What if the weight of V is strictly bigger than the weight of T? Why is that a problem?
Because V is our smallest character, or one of our smallest characters.
Right. So if weight of V were strictly larger than the weight of T, then T would be one of the smallest two characters.
Or the children of T would be the way smallest smaller character.
Right. So this can't happen. So what must be the case?
Weight of V equals weight of T.
Weight of V equals weight of T. So this can't happen by hypothesis that V and W are smallest leaves. Hence, the weight of V equals the weight of T.
Hold on. If T is a subtree,
Sorry. Yes, that's not true. That can't happen. The next conclusion, that was the wrong conclusion. What were you going to say, Josh?
oh, if T is a subtree, then how are we comparing its weights to begin with?
It just has Can we just work under the assumption that the weight of a node is just its frequency?
It is, yeah.
Right, so it's...
But T could also be...
T could be an interior node.
Interior node.
Right, in which case it's just defined the same way, right? It's still depth times, right?
Yeah, right, because it still would have been joined with, joined with W because it would have been the smallest guy. Yeah, so we're good. Okay. That can't happen by hypothesis. Where do I want to go next? I want to not jump ahead of myself here. So what this tells me is the net change is non-positive. Okay, so what does that do for us?
It's 0.
Must be 0 because the weight of Tm is minimal. Almost there. Oh, I'm overdue though. Okay, let me just really quickly run through this. Do the swap. And get a new tree. T double prime M. So we know that, sorry, we're not up to T double prime yet, we're just at T prime. Do the swap. The weight of T prime M is equal to the weight of Tm. And V and W are siblings. In T prime M. Okay, now look at, now we're ready to do what Luke wanted to do at the very beginning. Remove V and W from TH and T prime M. So remember where T prime came from? It came from swapping, making V and W siblings. Now I'm going to remove them from both the Huffman tree and T prime of M, which is a minimal tree. Take away 2 nodes, take away 2 siblings. What happens to the parent? It becomes a leaf in both of these guys, in both TH and T prime M. These guys are both Huffman trees. So we get T prime H and T double prime M are both Huffman trees. Sorry. This guy's still Huffman. This guy's minimal, yeah. I'm going to let you, because I'm out of time, I'm going to let you pick up from right here and think about it, and we'll come back and finish it off on Wednesday. But we're now into induction hypothesis territory, right? When we take away 2 nodes, the parent becomes a leaf node. How many leaves are in TH prime? N minus 1, right? And now we know that that's a minimal tree. So I'll finish it off on Wednesday, but think about it from there. This is what computer science really is. Just so you know.